upgrades. The main driver was it was unsupported hardware, unsupported and obsolete hardware. The DCS that was in use was a Toshiba Tosdic DCS, and it was 1970s, 1980s type technology, and they were running out of spares essentially on site. And there was also Modicon 984 PLCs throughout the process control system, and they had a separate chip system consisting of 5 984 PLCs as well across the particularly hazardous areas of the plant. During the project, they had an emphasis on implementing best practice control system design, focusing on high availability, maintaining the high availability architecture of the similar to the Toshiba system, but across controllers, networks, HMI application and hardware, and also power supply backups. And they wanted an integrated solution where the PlantPAx system really fit that bill quite nicely, extending into the safety process system as well. Also, there was a focus on functional safety compliance. So our customer chose to implement a 61508 functional safety compliant system. So our new system had to comply with those requirements from outcomes of HAZOPs that were undertaken by the customer, LOPA studies, and our safety system complied with all those requirements. And also this particular site had fairly unique hazardous areas that we had to ensure all the electrical design aspects within the process areas complied with current day hazardous area requirements. So the summary of the project, we were to deliver a new integrated control system across 17 process buildings, including the DCS upgrade, which is the Toshiba to the PlantPAx, sys controller upgrade, which is from old Modicon 984 PLCs to the Rockwell AADvance, operator interface upgrade, network infrastructure upgrade, including cabling, control room upgrade, complete refurbishment of the control room, and we delivered a simulation system for operator and maintenance training, but we also utilised that for our internal FAT purposes. So I'll go through a few of the control system stats. So the process controllers, there was over 3,200 DCS I/O across 12 PlantPAx PX controllers, and 5 of those controllers are redundant controllers. And the system consisted of over 400 sys I/O across 5 advanced controllers. The network infrastructure consisted of, this is the new network infrastructure, consisted of 11 Cisco 3750 managed switches at the distribution layer, forming a self-healing ring, which I'll show you a bit later on, and 15 Stratix managed Ethernet switches across the access layer. And we installed approximately 4 kilometres of fibre to connect the 50-hectare facility. The HMI infrastructure consisted of 10 physical host servers, and we implemented a virtualised system as well. So 10 physical host servers with 50 virtual machines installed across those servers, 7 virtually distributed redundant HMI server pairs, and the whole system consisted of 12 thin and 4 thick clients, HMI clients. Some of the other integrated software that we utilised, which was we used FactoryTalk Historian and Vantage Point for historical trending and reporting. FactoryTalk Asset Centre for asset management, backups of all the controller code, all the HMI code, all the switch configurations. We used VMware's vCenter for the virtual environment management, and Veeam for the virtual environment management backup. And we also implemented a redundant UPS architecture, consisted of 7 redundant and 11 non-redundant UPS systems, totaling of about 34 kilowatts of backup power, providing about 1 hour, in excess of 1 hour, of backup to all PlantPAx controllers, all HMI servers and clients, all network switches, and all process instrumentation across the whole facility. It was actually quite in excess of 1 hour, probably getting 2, 3, 4 hours in some areas. And the simulation system we delivered was a single virtual host running 9 virtual machines, 12 total, 9 concurrent virtual machines running, consisting of a domain controller, factory talk directory server, simulation server, engineering workstation, operator workstation, and 4 process automation system servers. We had 2 thin clients connected to that server, which was the operator workstation, HMI client, and the simulation management, which was basically the trainer, and the operator workstation is the trainee. Okay. The soft logics was used for the controller simulation, where we had 6 concurrent processes running, which is basically simulating 6 different areas of the plant at once. So they were all different areas of the plant were talking to each other. And the process simulation package that we used was PIX Pro, which basically had an OPC connection into the SoftLogix system to simulate the process actions or response. So I'll go through the control system architecture. We had a central control room sitting at the top there, and then 7 process areas scattered across the whole facility. And they were connected by, so these 3 stacks here were the 3750 Ciscos, providing the distribution layer connectivity. And down in the process buildings, we had Stratix, either single or redundant Stratix managed switches in a star topology, but redundant star topology. Our restriction here was being a brownfield site. We had to maintain and utilise existing conduits around the facility. If it was a brand new site, we probably would have had a self-healing ring or a number of self-healing rings. We had a number of installed 12, combination of 12 redundant and non-redundant PAX controllers, ControlLogix controllers, across the 7 process areas. 5 advanced controllers, 1 in the central control room, providing remote activation of critical functions like emergency stops, drown functions, things like that, and 4 particularly hazardous process areas. And they were also talking to each other. They were talking to their local ControlLogix controllers via CRP comms, and they're also talking to each other via safety communications, all on the same network. Then we had 7 area-based server hosts, virtual hosts, and two server hosts up in the control room. The 7 process areas were identical in structure, where we had a primary HMI server running, a secondary domain controller, and operator workstation in each of the 7 process areas. The reason why we had distributed servers is because if there was for whatever reason, if there was a connection severed between the control room and the process areas could still actually function, could run in isolation for them to be able to shut down safely. Okay. In the control room, one of the servers had the 7 standby HMI servers running, also the primary domain controller, Vantage Point server, and the Sys Engineering Workstation. And the second server had the Factory Talk Directory, Asset Center, Historian, Engineering Workstation, secondary domain controller, environment management using vCenter, and the Veeam backup system. Now, those 2 servers in the control room were in high availability mode. If one server physically fell down, the virtual machines running on that server would seamlessly be transferred and up and running on the other server without any loss of communication or function. And we had a combination of 4 thick clients in the control room, dual screen thick clients, 2 of which had a third 60-inch screen on the walls. And the process buildings had 9 dual screen clients amongst the local control rooms. And the whole system was backed up by a remotely located network access storage drive using the Veeam software. And the simulation system that we provided consisted of a server with all of these VMs running, 9 of which run concurrently, connected via a switch to 2 thin clients, one being the PIX Pro, where a trainer can manipulate process responses and trigger faults in the process, and the trainee, an operator and maintenance person, basically having the HMI screen in front of them. This is a photo of the original control room. You see it's quite outdated, quite cluttered, nice salmon pink walls, and fairly old screens and technology. New control room, nice sleek design. We gave a lick of paint, replaced the floor, replaced the lighting, brand new control desk, brand new chairs. They're very, very comfy chairs, probably too comfy for operators. We had 4 of these dual screen clients and the 60-inch screens there, and you can drag up HMI, different HMI pages, CCTV as well onto any of the screens. Our control panels, this is an example of the control panel. So we've got our redundant CPU controllers up the top racks and a couple of I/O racks, all connected via separate DLR device level ring network from the peer-to-peer or SCADA networks. This is an example of one of the AADvance panels. These particular panels were built by Rockwell as part of their delivery to us, and we basically put those in the same suite of the panels that we supplied directly. And basically we ripped out all the existing panels. We didn't have the day or few hours turnaround requirement that Nearstar had, so we ripped out all the panels and put new ones in and re-terminated all the multi-cores. Sorry, and that's an example of one of our IS panels, new barriers and IS ducting there. Example of one of our networks panels. We've got our redundant UPS bank and batteries at the bottom here. That's one of our local servers. That is a CCTV controller, and there's a couple of redundant Stratix managed switches, and then our copper and fibre patching and phobots at the top there. And that's an example of one of the centralised services buildings where we've got up to 7 area buildings, fibre patching, cabling coming into here. So phobots of 7 buildings coming into here, and then fibre connected to a couple of stacks, redundant stacks of the 3750 Cisco switches at the distribution level. So some of our unique requirements and challenges. It's a major hazard facility, this particular one, so that equates to a high compliance project. A lot of hoops to jump through, real focus on validation of old for new functionality. A lot of unique hazardous areas, a lot of mixed zones, not only vapour, not only dust, combination of all, and that equated to quite some challenging electrical design aspects for the equipment that we actually replaced within the process buildings. Alignment of customer expectations around the operator interface mainly. It's a 20 to 25-year-old facility, so there's a lot of pre-existing expectations. The operators have been there for a long time, and they do things a certain way that the old technology only allowed them to do, but now we've got new technology, new ways of presenting things on mix, and to maintain their confidence level, was a challenge, and basically trying to merge the old to new technologies and practices together to have a system that fit the bill was a bit of a challenge. But that was basically continuous engagement with the operators to get their buy-in. Old trip system versus new safety instrumented system. We had to maintain compliance with 61508. We had to, the functionality of the new trip system had to be in line with the SRS and the HAZOPs and SRS that was developed, but we also had to ensure like-for-like functionality of the original trip system. You know, it's a hazardous process, so the customer really needed to be comfortable that we didn't miss any interlocks out, any safety critical interlocks that may not have appeared as part of the safety requirements of the new system. And obtaining a baseline, the state of the original documentation being a 25-year-old facility, it's patchy, as you can appreciate. So trying to identify what that baseline is to build our new design from, and also proving lifelike functionality from inaccurate or non-existent functional descriptions proved to be a challenge. So there was some fairly unique ways of trying to prove that like-for-like functionality that had to be implemented. PlantPAx Overview, software versions, we used FactoryTalk View version 7, PlantPAx System Release 3, and RS Logix version 20. The engineering tools that we've utilised is Logix View Utility, LVU, for instantiation of all PlantPAx code templates within the controller, and the alarm generation within FactoryTalk View. LVU is a hell of a lot more capable, but due to some of the customisation that we needed to implement, driven by customer requirements, we weren't able to use LVU fully. The online config tool, OCT, we use for updating PlantPAx controller device tags, and we utilised it for the validation purposes. We uploaded device tag values into test sheets and device test sheets and things like that. That was a very handy tool. Alarms were provided by a FactoryTalk Alarm Event Server. Time-critical alarms were implemented via controller-based alarms. And alarm metrics reporting was provided via Vantage Point out-of-the-box alarm reports. Trending was implemented via real-time and historical trends via FactoryTalk Historian. We did customise PlantPAx device objects due to specific customer requirements, trying to get that old for new expectations working. And we built custom macros and VB code macro modules for tag search functionality, alarm silence all functionality between different clients within different buildings or the same area, and trend template management, display time, alarm zoom control, and tag navigation from the trend pages. The top 5 PlantPAx tips. Where possible, avoid library object customization, just so you can maintain an easy upgrade path. Your customers really need to know the implication of modifying the library objects. Carefully consider PlantPAx controller sizing requirements. Our experience is that you wouldn't fit a PlantPAx system, even a small one, in anything less than an L72 controller. Most of ours are L73s. Carefully consider FactoryTalk View SE page license requirements. There's a lot of faceplates, which is a page essentially in their page count. So our experience is you wouldn't get away with any less than a 100-page license per project. We standardised at 250-page licenses across all 7 areas, and realise the benefits through use of engineering tools like LVU or the ACM that's coming up, and the online config tool. That's where you get the really engineering savings using those tools. And last one is utilise Rockwell's PlantPAx system review services. Rockwell provide these services to critically assess your design, your architecture, software, hardware architecture. They'll give you recommendations, and it's good to get that that Rockwell stamp of approval before you start investing and starting purchasing licenses and hardware and investing. Some example screenshots, the HMI. It's a mimic trend page with series of customised functionality here. The top one is basically opening up faceplates of tags that are displayed on the trend, some saving of alarm templates, trend templates, and changing the display time and range directly on the page instead of going into the menus. And an example of one of our controller and status pages. Why AADvance? So Sage, before this project, Sage hadn't had any experience with advanced controllers. I believe this particular site was the first implementation of a controller in Australia. So it's fairly new to, very new to Sage, quite new to Australia. So we thought we'd put it to the test. We assessed it against other controllers that Sage has had experience with. So we put it to the test against, just giving you the Rockwell control logics, the SIL2 architecture, Rockwell guard logics, and the Siemens S7300 fail-safe systems. We found the Rockwell control logics was not best fit for application because we would have struggled to achieve the high SIL2 requirements of this project. The control logics is suitable for SIL2 implementation, but when you take into account the inputs, safety inputs, and the actuators with the logic solver, the resultant PFD would fall short of a high SIL2 system. The architecture for SIL2 applications within control logics is quite complex, and that also equates to a large panel footprint. And control logics is only really suitable for de-energized to trip functions, which we have a couple of energized to trip functions within this system. So instead of failing to off, we needed to make sure that we maintained or energized a function to trigger a safety function. And there was no real cost benefit either in terms of hardware cost between AADvance and control logic SIL2. The guard logics, again, it's only suitable for de-energized to trip functions, really is suitable for machine guarding. Okay, the predominant failure mode is off. That type of controller looks for any reason to shut down. So we were concerned about spurious trips. And also there was no real cost benefit in terms of hardware between guard logics and AADvance. Siemens, our assessment was quite similar to the guard logics, except the additional one is interfacing to factory talk environment wouldn't be elegant. Siemens talking to Rockwell, it's like Ford and Holden. It just doesn't go together very well. So when we assessed AADvance, it is suitable for energized to trip functions. It is, has a simple architecture even for SIL2 applications, which also equated to a smaller footprint, which was in some of our areas was quite an issue. It's built for process safety applications, so it's very good for analog processes. It had superior availability and redundancy above and beyond the other systems, up to 2 out of 3 with diagnostics voting architecture, which is the triplication architecture. Richard will go into that in a bit more detail later. And the interface into factory talk environment is via CIP communications, either single or redundant controllers. So it made interfacing onto the same network infrastructure very simple. Okay, that concludes my part of the presentation.